So now that we have all of our technical theory built up, let's actually apply this to an actual example. So, and this is an example that will figure out where the critical points or where the maximum and minimum values are without actually even knowing what the function looks like. So suppose we want to find the maximum and minimum values of the function f of x is equal to 16x cubed plus 63x squared minus 232.5x minus 200. And then we're looking for the maximum and minimum values on the closed interval from -4 to 2. So x is only defined on this closed interval. First of all, we note that we have a cubic polynomial. And polynomials are continuous, so therefore we have a continuous function. It's defined on a closed interval. So because of the extreme value theorem, we know that it does possess a global maximum and a global minimum. Now, two of the possible places where this can occur are exactly the two boundary points, -4 and 2. So those are already in our suspect list. The other possible places are located wherever this function has a critical point. So to solve for the critical points, we take the derivative and set it equal to 0. So the derivative of this is going to be f prime of x. 16 times 3 is 48x squared. 63 times 2 is 126x minus 232.5, and then the derivative of 200 is 0. So the derivative is 48x squared plus 126x minus 232.5. And to find the critical points, we set the derivative equal to 0 because we're looking for the points where the function has 0 slope, because those might be the maximum or minimum values. Right? And it makes sense because whenever the derivative goes from positive to negative, the function is going from increasing to decreasing. So when the derivative is going from positive to negative, it's going to pass through 0. So as the function goes from increasing to decreasing, the derivative is passing through 0 right at the peak of that. And then similarly, when the function goes from decreasing to increasing, the derivative is going from negative transitioning into positive, so again it's passing through 0. So that's why we look for the zeros of the derivative. So we can solve this using the quadratic formula, minus 126 plus or minus the square root 126 squared minus 4 times 48 times negative 232.5, all divided by 2 times 48, which is 96. Okay, so 126 squared is 15,876 plus 4 times 48 times 232.5. That gives us 60,516, and the square root of that is an even 246. So the critical points are at minus 126 plus or minus 246 over 96. Now this looks like it can be reduced, and when we simplify this, we can only simplify it if we can take out the same from both of these terms. Obviously everything you see here is divisible by 2. Let's see if it's divisible by 4 as well. 126 over 4, 31.5, not divisible by 4. So let's cancel out a common factor of 2. So 126 over 2 is going to be minus 63 plus or minus 246 over 2 is 123. And 96 over 2 is 48. Maybe everything's divisible by 3. It kind of looks that way, doesn't it? So 63 over 3 is 21. So we get minus 21 plus or minus 123 over 3 should be 41. Yeah, 41. So plus or minus 41. And then 48 over 3, 16. So 16 is just divisible by 2 a number of times. 2 times 2 times 2 times 2. And the numerator is not divisible by 2, so that's the best. So negative 21 minus 41. So if we look at the actual values, negative 21 minus 41 is going to be 62. So we get minus 62 over 16, and then negative 21 plus 41, that's the same as 41 minus 21, which is 20. So that's 20 over 16. And then these can individually be simplified. 62 over 16 is going to be negative 31 over 8, and then 20 over 16 is 5 over 4. So those 2 points, 31 over 8 is going to be at negative 3.875 and then 1.25. So those are the 2 critical points. And we also want to check that our critical points are actually in the interior of the domain, because with this restriction, this function can't actually be defined everywhere. It's only because of this restriction that we say that it's only defined between minus 4 and 2 that it's that way. So we want to make sure that these critical points, which are only obtained by blindly taking the derivative of, maybe not blindly, but by just taking the derivative, setting it equal to 0, we have no guarantee that those derivatives lie within the interval from minus 4 to 2. But they check out, they're both between negative 4 and 2. So they're both greater than negative 4 and less than 2. So next we have our 4 suspects. So our theorems and our everything we've discussed so far tells us that the extremum have to be either at these 2 critical points or at the 2 boundary points. So then we just plug everything in. F of minus 4, f of minus 3.875, f of minus 1.25, and f of 2. So these points when we plug them in, well, we can actually go through and solve this equation several times. And I went ahead and did that. I paused the camera. So f of negative 4 is 714. F of negative 3.875 is 715.95 ... F of negative F of positive 1.25 was negative 360.9375, and f of 2 is negative 285. So this gives us a pretty good picture of what the function looks like. So f of negative 4 was up here at 714, so that's at negative 4. And then at a little while later it has a maximum just at negative 3.875. So 1/8 of a unit later we have a maximum at 715, and then it decreases and it has a minimum down here at 1.25, and then it comes up a little bit for f of 2. So at 2 we have an output of negative 285. At 1.25 we have our minimum, which is at negative 360.9375. Our maximum is right here at negative 3.875, and the maximum is 715.9531249, and we have a local minimum right there at 714. So because of the theory, we know that this is basically what it looks like. So this endpoint is a local minimum, this is a local minimum, and then the critical point at negative 3.875 is a local maximum, and the critical point, or the boundary point 2, is a local maximum. So then we have maximum, maximum. Moreover, we know that it has a global maximum and a global minimum because it's a continuous function on a closed interval. So this must be the global maximum. And then this one must be the global minimum. So the absolute smallest value of this function on this interval is negative 360.9375, and occurs at x is equal to 1.25. And the absolute largest value occurs at negative 3.875. So it's pretty amazing that just without using any sort of technology or calculator, We just look at this and we're able to figure out where the maximum and minimum values are. So that's the sort of thing that we can do with these theorems.